We would now discuss elementary queuing models. There are a lot of queuing models available based on a combination of all the characteristics of your calling population and your service facility. But we are just going to focus on 6 of the most used queuing models in business. In all of the queuing models, following are the notations that would be used. First is L sub q. L sub q represents the expected or mean length of the queue or the number of calling units in the queue. L sub s represents the expected number of calling units in the system. That is, number in the queue plus number being served. So let me differentiate between the two. Let's say you are in a bank branch with 3 tellers and there are 5 people in line. L sub q would be equal to 5, which would be the number of people in line. L sub s is equal to 8. That would be number in line, which is your 5, plus number being served. Since there are 3 tellers, then you assume that there are 3 people already being served by the 3 tellers, because the 5 would not continue lining up if there is already an available teller to serve them. Therefore, L sub s is equal to 8. That's the difference between L sub q and L sub s. Next, we have W sub q, which is the expected or mean time spent waiting in line, or just queuing time. W sub s is the expected or mean time spent in the system, which includes waiting time in the queue as well as service time. You also have lambda. Lambda is the mean arrival rate or the number of calling units per unit of time. Mu is the mean service rate or the number of calling units served per unit of time. 1 over mu is the mean service time for a calling unit. S represents the number of parallel or equivalent service facilities in the system. In a bank branch, based on practice in the Philippines, there are some branches wherein during peak periods, tellers were only tasked to accept deposits, or another teller would be tasked to just process withdrawals, or another teller would just be tasked to purely process checks. In our discussion, however, we are assuming that each teller can perform all the tasks required from a teller. P of n represents probability of having n units in the system or the probability of having a certain number of customers in the facility. And then you have rho. That is not the letter P, that is the Greek symbol rho, R-H-O, which represents the server utilization factor, or the proportion of time the server can be expected to be busy during a given day. So given all those notations, we now begin with the first queuing model, which is your basic single server model, or there is only one service provider in your facility. The assumptions of this model are as follows. You have Poisson arrival process, exponential service times, single server, first come, first served service discipline, infinite source, infinite queue, and patient calling units. So as I mentioned in the previous video, queuing models would simply just be a matching process between the assumptions in a given scenario versus the assumptions of a queuing model. So again, the process in solving queuing problems would be to first identify the assumptions in the scenario that you are asked to analyze, and then match the assumptions in such a scenario versus the assumptions of a particular queuing model. So, if the assumptions in the problem you are analyzing matches the assumptions of the basic single server model as shown in this slide, then following are the statistics that you now have to determine. First, the probability of 0 calling units in the system, or the probability that there is no customer in the facility. That is computed as P of 0 equal to 1 minus the quantity lambda over mu. Next, the probability of n calling units in the system, P of n, is equal to P of 0 multiplied by the quantity lambda over mu raised to your assumption for small letter n. This now determines the probability of a certain number of customers in the facility, depending on what is your assumption for number of customers. Next is the proportion of time the server is busy. Rho is equal to lambda over mu. Followed by expected number of calling units in the system. L sub s is equal to lambda all over the quantity mu minus lambda. Then we have expected number of calling units in the queue. L sub q is equal to lambda squared all over the quantity mu multiplied by the quantity mu minus lambda. Expected time in the system is computed as W sub s equal to 1 all over the quantity mu minus lambda. And then the expected time waiting in line, W sub q is equal to lambda all over the quantity mu multiplied by the quantity mu minus lambda. Let's apply this particular model in a scenario. A particular toll road has one attendant at an exit lane. Cars arrive at the toll gate in a Poisson fashion at a rate of 120 cars per hour, and it takes the attendant, on the average, 15 seconds to service a car. Service times are exponentially distributed. Assumptions of an infinite calling population and an infinite queue are reasonable. So based on the scenario, what are the basic queuing statistics for this system? So we begin the process by first identifying the given data. Let's begin with lambda. Lambda is your arrival rate. So based on the second sentence, it says there that cars arrive at the toll gate in a Poisson fashion at a rate of 120 cars per hour. So your lambda is 120 cars per hour. Next is your mu, or your mean service rate. Okay, same sentence. Latter part says that it takes the attendant on the average 15 seconds to service a car. So your mu is equal to 15 seconds per car. Now, if you would look at the data we have so far, they have different units. And as you know, basic mathematics dictates that before you proceed with any solution methodology, you first have to have a common unit. So let's first transform our data into a common unit. Let's say minutes or cars per minute. So the first value, your lambda, if you transform that in terms of cars per minute, since 1 hour is equal to 60 minutes, then that would be equal to 2 cars per minute. And then for your mu, if originally you can service a car in 15 seconds, how many cars can you service in 1 minute? Since 1 minute consists of 60 seconds, then that means your mu is equal to 4, or 4 cars per minute. So now that we have the data in a common unit, then we can proceed with the required statistical requirements under the basic single server model. Beginning with the probability of 0 calling units in a system. P of 0 is equal to 1 minus lambda over mu. Substituting the data we have in their common unit to the formula, then this would be equal to 1 minus the quantity 2 over 4, or P of 0 is equal to 1/2, or 50%. So 50% of the time there is no car passing through this particular system. Okay? This is based on the values of your lambda and your mu, which are averages based on observation. Meaning those values were derived based on data collected over a certain period of time, let's say over a week or over a month, and those values are averages. Therefore, your succeeding results from the use of the formulas would also be in the form of averages. So on the average, half of the time there is no car passing through this particular toll system. For the second formula, this one is something that you are going to use if there is a specific statement in the problem requiring you to determine the probability of a certain number of calling units in the system. If there is no such requirement in the scenario provided to you, then you can skip this formula when you are using the basic single server model. Next is the proportion of time the server is busy. Rho is equal to lambda over mu. Again, substituting the data we already have, your lambda is equal to 2 while your mu is equal to 4. So that gives us 1/2, or again 50%, which is quite reasonable considering that 50% of the time there is no customer going through the system, as we found earlier, which is your P of 0. Therefore, 50% of the time, your service provider assigned to that particular toll road is not doing anything. Then we have the expected number of calling units in the system. L sub s is equal to lambda over the quantity mu minus lambda. Again, substituting the data we have, you would have 2 all over the quantity 4 minus 2. Or this would give us a value of 1 car. There is 1 car on the average in the entire system. Next, expected number of calling units in the queue, or L sub q. Again, substituting the data we have to the formula, you would have 2 squared all over the quantity 4 multiplied by the quantity 4 minus 2. And then solving for this, you are going to get an L sub q value equal to 1/2 of a car. So on the average, there is half a car in the system. Again, the values we get are averages. Okay, but if you would like to imagine, how is it possible that there is half a car waiting and yet there is an entire car in the system? Okay, so if you would like to really imagine this one, if you go to a particular toll booth, normally the one who pays the toll is the driver who is seated at the front of the car. And passengers at the back of the car, in effect, are merely waiting until the driver who is in front of the car has paid the toll. So that means half of the car is waiting and yet the entire car is in the system. So that is the philosophical explanation for the values that we got here. But again, the values here are averages. Next, expected waiting time in the system, W sub s. Substituting the values or our data to this particular formula, this would be equal to 1 all over the quantity 4 minus 2, or 1/2 of a minute. Of course, you don't maintain the value as 1/2 of a minute, because if you provide that information to somebody who's going to use it for decision making, he would still have to process it. And most likely, he would think that 1/2 of a minute, that would be around 30 seconds. So might as well process it for him. Or transform your final answer into a unit that is readily usable for decision making. And then the last requirement under this queuing model, you have expected time waiting in line, or W sub q. Again, substituting the data we have, then you would have 2 all over the quantity 4 multiplied by the quantity 4 minus 2, or 1/4 of a minute, or 15 seconds, which is exactly the service time provided per car, or the original data, which is 15 seconds per car. Okay, so these are the values that you're going to derive when you use the basic single server model. They are still subject to interpretation depending on what is required by the decision maker. For example, if there is a request for an additional attendant in this particular toll road and you are the head of human resources, would you grant the request? Based on the data you have derived, it would actually depend. The usual practice is that a survey would be made among all the customers that regularly use the toll booth. So if based on their response to the survey, they say that these waiting times that we derived are still acceptable to them, then as the head of human resources, you can make use of these computations or these data together with the results of the survey to justify your decision not to allow the request for an additional attendant, because based on survey, the values you have derived are still acceptable to your customers. However, if the survey would result to the fact that your customers do not already see these values as satisfactory to them, or if they find these values already too long, then again, as head of human resources, you can make use of these computations together with the results of the survey to justify your decision to allow the hiring of an additional attendant. Okay? So it actually depends. So usual practice is a survey would be made, or there would be some sort of internal standard set by the company, or there would be an industry standard followed by most of the players in the same industry. Okay, so you have to be aware of those standards. Otherwise, the safest is still the survey among consumers, but that would take time in order for you to gather the required data. This is your basic single server model. Let's proceed with the next one, which is your multi-server model with Poisson arrivals and exponential service times. The assumptions of this model are identical to those of the basic single server model, except that the number of servers is now assumed to be greater than 1. Also, it is assumed that all servers have the same rate of service. So, if the assumptions of the basic single server model, other than the fact that you only have one server, has been satisfied based on your analysis of the scenario you are trying to analyze, then following are the statistics that you have to determine. The probability of 0 calling units in the system is now computed as P of 0 equal to 1 all over the quantity summation from small letter n equal to 0 to s minus 1 of the quantity lambda over mu raised to your assumption for small letter n over small letter n factorial plus the quantity lambda over mu raised to s over s factorial multiplied by the quantity 1 minus lambda over s multiplied by mu raised to negative 1. I hope you still recall how to do your factorial notation. Next, the probability of n calling units in the system. If your assumption for small letter n is less than s but greater than or equal to 0, then P of n would be computed as the quantity lambda over mu raised to your assumption for small letter n over small letter n factorial multiplied by your P sub 0 or P of 0 value. Now, if your assumption for small letter n is greater than or equal to the value of your s, P of n would then be computed as the quantity lambda over mu raised to your assumption for small letter n over s factorial multiplied by s raised to small letter n minus s multiplied by P of 0. And then the proportion of time the server is busy is now computed as rho is equal to lambda over s multiplied by mu. That is assuming each server has the same mean service rate of mu units per time period. Next is the expected number of calling units in the queue. L sub q is equal to P of 0 multiplied by the quantity lambda over mu raised to your s multiplied by rho all over s factorial multiplied by the quantity 1 minus rho quantity squared. Followed by expected number of calling units in the system, L sub s is equal to L sub q plus the quantity lambda over mu. Then you have expected time waiting in line, W sub q is equal to L sub q over lambda. And expected time in the system, W sub s is equal to W sub q plus the quantity 1 over mu. Okay. For this particular queuing model, you have to be very careful in solving for your P of 0. Why? If you look at the bottom statistical requirement, W sub s is dependent on the value of your W sub q. W sub q, in the meantime, is dependent on the value of your L sub q. And your L sub q on top is dependent on the value of your P of 0. So if you commit a mistake in computing for your P of 0, everything else would be a mistake. So you have to be very careful in using this particular queuing model. Let's apply. Let's go back to the original example, but this is now changed a bit to comply with the assumptions of the multi-server model. So again, I'll repeat. A particular toll road has 3 attendants at an exit lane. Cars arrive at the toll gate in a Poisson fashion at a rate of 600 cars per hour, and it takes the attendant on the average 15 seconds to service a car. Service times are exponentially distributed, and assumptions of an infinite calling population and an infinite queue are reasonable. So based on the given scenario, what are the basic queuing statistics for this system? So since in the sentence or in the first sentence it already says there that you are dealing with a scenario where you have 3 attendants, then automatically the assumption here is multi-server. Let's apply. So we again begin the process by first identifying the given data. First is your lambda or your arrival rate. Your arrival rate is now 600 cars per hour. Then you have your mu, which is your mean service rate, which is still your 15 seconds per car. So again, if we transform the two values into a common unit, which is cars per minute, the first value would become 10 cars per minute, while the second value would still be your 4 cars per minute. And then another information provided in the given scenario is that you have 3 attendants, so your S is equal to 3. Given those values, then we can now proceed with the statistical requirements beginning with your P of 0. So substituting the data we have to this particular formula, then this would be equal to, or your P of 0 is equal to 1 all over the summation from n equal to 0 to s minus 1, where your s is equal to 3. So the upper bound of your summation symbol would be 3 minus 1, or 2. And then you have lambda over mu, which is 10 over 4 raised to n over n factorial, plus lambda over mu is 10 over 4 raised to s, which is 3 over s factorial, which is 3 factorial, multiplied by 1 minus 10 over 3 multiplied by 4, and then raised to negative 1. Okay. Let's proceed. So again, P of 0 would now be equal to 1 all over. Okay. For the summation portion of the denominator, you are supposed to analyze the first part of the denominator beginning with the assumption that your n is equal to 0, which is the lower bound of your summation symbol, until you reach the upper bound, which is equal to 2, with an increment of 1 unit at a time. Meaning, you're going to begin with n equal to 0, followed by n equal to 1, followed by n equal to 2. You are not merely going to analyze the first part of your denominator with n equal to 0 and then immediately n equal to 2. The increment is by 1 unit. So let's proceed. Beginning with n equal to 0, then the first part of your denominator would be 10 over 4 raised to 0 over 0 factorial, which is equal to 1, because any number raised to 0 is equal to 1. And then 0 factorial is also equal to 1. So you will end up with 1 over 1, which is equal to 1. If n is now equal to 1, then the first part of your denominator would be 10 over 4 raised to 1 over 1 factorial. 1 factorial is equal to 1. So you would end up with 10 over 4 raised to 1, or simply 10 over 4. And then if your n is now equal to 2, then you would have 10 over 4 raised to 2 over 2 factorial. Your 2 factorial is 2 multiplied by 1, therefore that is equal to 2. So you would have 10 over 4 raised to 2 over 2. Moving now to the second part of your denominator, you have there 10 over 4 raised to 3 over 3 factorial. So you would have 10 over 4 raised to 3 over 3 multiplied by 2 multiplied by 1, or 6, multiplied by the quantity 1 minus 10 over 12 raised to negative 1. The latter portion of your denominator, which is 1 minus 10 over 12, is computed as 12 over 12 minus 10 over 12, or 2 over 12, or 1 over 6. Raised to negative 1 means you have to get the reciprocal of that fraction. And the reciprocal would be equal to 6, which is something that you can cancel out with the denominator of the one that is at its left side. And then you just have to compute. you are going to get the value of P of 0 being equal to 0.044943882, or in percentage form, this is approximately 4.5%. This is the probability that there is no car passing through the system. So, if in our first example earlier, the P of 0 is equal to 50%, that means that that particular toll system is not too busy. Whereas here, the P of 0 was derived to be 4.5%, which is relatively small, which suggests that this particular toll system is very busy. Next, the probability of n calling units in the system. Again, similar to the previous model, if there is no specific requirement stated in the problem requiring you to determine the probability of a certain number of calling units in the system, then you can skip the use of this particular set of formulas. Next is the proportion of time the server is busy. Rho is equal to lambda over s multiplied by mu. So substituting the data we have already determined earlier, your lambda is 10 over s is 3 multiplied by mu, which is 4. So your rho would be equal to 5 over 6, or approximately 83.33%. Next, expected number of calling units in the queue. Substituting the values we have already derived, your P of 0 is your 0.044943882 multiplied by lambda over mu, which is 10 over 4, raised to the value of your s, which is 3, multiplied by your rho, which is 0.83 bar. When I use the bar notation, that means the true value is 0.83333333. Okay, so in your case, it is highly suggested that you maintain the required number of decimal positions we have agreed upon in your computations in order for you to avoid rounding off errors prior to reaching the final answer. So divided by s factorial, which is 3 factorial, multiplied by 1 minus rho, or 1 minus 0.83 bar quantity squared. Then again, simply compute. You're going to get an L sub q value equal to 3.51123595 of a car. Again, the values we get here are all in averages. Next, expected number of calling units in the system, L sub s, which is equal to the value of your L sub q plus lambda over mu, which is your 10 over 4. This would give us a value of 6.011235595, or approximately 6 cars. Number of calling units in the system. Next, expected time waiting in line, W sub q is equal to L sub q over lambda. Our L sub q was derived earlier to be your 3.51123595 divided by your lambda, which is 10, would give us a waiting time in line equal to 0.3511239 of a minute, which we need to transform into something more meaningful. So if you multiply that value by 60, then you're going to get 21.07 seconds. And then the last requirement under this queuing model is the expected time in the system, or W sub s, which is equal to W sub q plus the quantity 1 over mu. For computing the W sub s, make sure that the value that you're going to get for W sub q is the one in its original unit, which is in terms of minutes, not the converted one, which is in terms of seconds. Because if you continue with the formula, part of the formula is your mu, and your unit for mu is cars per minute. So you still have to have the W sub q in minutes in this formula. And then simply compute. This would give us approximately 36.07 seconds. Okay? So again, these are the values that you're going to derive using the multi-server model. It would now depend again on how you're going to make use of these values in defending your decision. So if these values that we derived in terms of waiting time in the line as well as waiting time in the system are still acceptable to the customers who make use of this particular toll system, then you can make use of these computations together with whatever survey data you have to justify your decision not to add another attendant. Now, if the values that you have derived here are deemed very, very fast, based, let's say, on a particular standard, then you can make use of these computations to justify your decision to reduce the number of attendants that this particular TOS system currently have. Okay? So again, it depends on what is your objective, but these are the data that you can derive using your multi-server model. The next is single server model with arbitrary service times, which I'm going to discuss in another video.